This is like the history chapter. Again, I'm not going to quiz you on these guys' names or when they lived or what they did or anything. So a guy named J.J. Thompson, he lived in the late 1800s, early 1900s. He made a cathode ray tube. So this is a glass tube that's partially evacuated, and it has a little bit of gas inside of it. And it's got electrodes at each end. And if you apply a high voltage to it, you can see a ray that goes from one end to the other. So that bit of light there, that's the cathode ray. That's an actual picture of one. Here is an illustration. So here we have this ray. You get this glowing, this light that happens. When you turn it off, there's just gas there. There's nothing. It's not like there's a light, a filament in an light bulb or anything. It's just gas. So those cathode rays were composed of particles, and they always traveled from the negative end, the cathode, to the positive end, the anode. And since they came from the negative end, they came from the cathode, they're called cathode rays. So Thompson found that the particles in those rays had particular properties. They traveled in straight lines. They were independent of the composition of the material from which they originated. They're coming out of the cathode. The cathode has to be a metal of some type to conduct electricity. But it doesn't matter what kind of metal it was, the cathode rays that came out all behaved the same way. And those cathode ray particles carry a negative electrical charge. So they carry negative electrical charge. So we need to have a brief visit to physics and talk about electrical charge. Electrical charge behaves a lot like magnets, okay, magnetic charge, which we all love to play with as kids. They're still kind of fascinating, right? So, the magnet will stick to the refrigerator, but it won't stick to the wall. It's kind of fun. So we can have positive and negative electrical charges, which would be like the positive and negative ends of magnets. And if you bring them together, they will be attracted to each other and stick together. So opposite charges attract each other. Like charges repel. So two positive charges, you're not going to be able to squish them together because they're trying to get away from each other. Same thing with the negative. My kids had Brio trains, or some of them were knockoffs, but those little trains that were connected with magnets, right? But you had to put the cars the right direction, and then they would just click and stick to each other. If you turn the car around, you could actually push the car without it touching the other car because the magnets were both north or south poles and they would repel each other. So electrical charges do the same thing. And if we have positive and negative electrical charges of the same magnitude, then they would add to zero when they're combined. So Thompson measured the charge to mass ratio of the cathode ray particles by deflecting them. He was able to, they travel in a straight line, but by using electric and magnetic fields, he was able to bend them. And by that method, he couldn't determine the charge or the mass, but he could find the charge to mass ratio. And this is the value that he measured. Coulombs is just a unit of charge. It was negative 1.76 times 10 to the 8th coulombs per gram. So this is the kind of a apparatus that he used. So he's generating his cathode ray here, shooting it through these electric and magnetic fields and causing them to bend. So that ratio implied that those particles making up the cathode ray were about 2,000 times smaller, lighter, less heavy than hydrogen, which is the lightest known element. So apparently, he was creating in this cathode ray something that was much smaller than an atom. And this was incredible, because this showed that the indestructible atom can be chipped away. You can knock things out of it. Yes?
So that little line in the cathode ray was like a line of electrons?
It's a line of electrons.
And become like separated from the atoms, or like how is it shown? Like,
Yeah, they get separated from the atoms. Yeah. Yeah, this is really kind of crazy. So he had discovered the electron. Electron is negatively charged, it has very low mass, and is present within all atoms. This is why when he used different kinds of metals, he got the same kind of array with the same properties, because all atoms have electrons. And what you're doing in that cathode ray is you're knocking electrons out of atoms. So this was the first evidence that all atoms are formed from the same particles. Milliken did an experiment with oil drops. So we got this, we have a mass to charge ratio, but they'd really like to find out, well, what is the mass and what's the charge of this thing? So he did this oil drop experiment, which allowed him to figure out the charge of a single electron. And then from the ratio, he could find its mass. So we'll look at the video in just a minute. Hopefully that one hasn't been privatized. So here's an atomizer, much like you would use for perfume, to take this oil and make a really fine mist of droplets. And those, of course, are going to get sprayed out, and then they're going to fall like everything else does because of gravity. So they're going to fall onto this plate. There's a little tiny hole in the plate. Some of them will hit the hole and fall straight through. The rest of them are just making an oily mess up there. This plate has a positive charge on it. The plate at the bottom has a negative charge. As those drops fall through from the first plate to the second plate, he zaps them with ionizing radiation to give them a charge. And then he fiddles around with the relative charges, because these are going to be negatively charged, and so they're going to be repelled by this plate and attracted to that plate. And if you get the charges just right, you can hold that particle suspended in the air. It's really kind of crazy. You know, some guy thought this up.
Right, they're like super ahead of their time.
Yeah, I mean, these people, barely knew what electricity was, right? Probably lived in a house without running water. I mean, just 1909. It was a long time ago. A lot has happened since then.
In a series of experiments carried out between 1908 and 1917, R.A. Milliken succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Milliken was able to determine the mass of an oil drop from its terminal velocity. Next, Milliken used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Milliken could solve for Q. which is the charge on the drop. Milliken found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Milliken concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thompson using a cathode ray tube, Milliken was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Yeah, so that's kind of your more typical science video, right? I'm not sure if that was a actual person or a computer saying that, but the equations and how they derived that are not something you need to worry about. If you're into science and physics and stuff, you probably understood some of that and you're thinking, wow, that was really cool. And if you aren't, you're like, I didn't understand that. It's okay. We're not going to do any calculations like that. But the idea here is that when he zaps these droplets with ionizing radiation, they're going to have a certain number of extra electrons. And so a droplet might have a -3 charge or a -4 charge. And so he could measure the actual charge by looking at what the charge on the plates needed to be to keep it from falling. And so he's got all these numbers, and then what he found was a common factor for all of them. And that common factor was the charge of one particle. Everything else was a multiple of that, because you can't have 1.5 electrons. You got 1 electron or 2 electrons. Right? So that's kind of what they said in the video. Measured the strength of the electric field needed to halt the fall, figuring out the masses of the drops. They could measure the radius and density of each drop, or they could also look at the terminal velocity. So you could calculate the charge. And all of those charges were whole number multiples of this number. So that's the charge on a single electron. And then knowing the ratio, they were able to calculate the mass. 9.1 times 10 to the minus 28 grams. You do not need to know either of these numbers.